Hi everybody, I am Anthony Santosh, Assistant Professor of Chemistry in St. Joseph College of Arts and Science. I am handling physical chemistry. Let us discuss one topic in physical chemistry. Now we are going to discuss the phase rule in physical chemistry. It is usually termed as Gibbs phase rule because it was enunciated by J.W. Gibbs, Josiah Willard Gibbs, in the year 1876. While investigating heterogeneous equilibria, he found this relation to explain the chemicals present in the system which are within equilibrium among themselves. Okay, now the phase rule is an important tool used for quantitative treatment of systems in equilibrium. So we know different kinds of systems. In earlier videos we studied that, and the phase rule enables us to predict the conditions that must be specified for a system to exhibit equilibrium. Okay, so what is homogeneous, what is heterogeneous? Homogeneous means uniform throughout. Homogeneous means homo means same. Homogeneous means uniform throughout, same throughout. And heterogeneous, hetero means different. So more than, if there is more than one phase present in the system, then that will be called heterogeneous system. System can be classified in this manner also: homogeneous system, heterogeneous system. Okay, we will see some other examples when we discuss into other parts. And it was first explained by this scientist Josiah Willard Gibbs, and he gave two kinds of phase rules to explain their complete internal equilibrium within the systems. Okay, so what is that? F is equal to C minus P plus 2. This is normal form of Gibbs phase rule. This is normal form of Gibbs phase rule. And what is the reduced form? This constant value of 2 is reduced to 1. So F is equal to C minus P plus 1 is the reduced form of Gibbs phase rule. Okay, so why there is a need for this rule? For a two-component system, for a heterogeneous system in some cases, we need the reduced form of Gibbs phase rule. So using this Gibbs phase rule, we can find the value of F. Okay, in the case of normal form, it is F is equal to C minus P plus 2. Using the values of component and phases, we can find the number of degree of freedom. And in the case of reduced form, that is condensed phases, by applying the number of components value and the number of phases value, we will be getting the value of F. What is F? F is the degree of freedom. F is the degree of freedom. Okay, so with these things we can get the value of F. But before going into that, we should know what is F, what is C, and what is P, and we should get a clear idea about these letters. What is F? F is degree of freedom or number of degrees of freedom. Degree of freedom or number of degrees of freedom. What is C? It is component or number of components. What is P? It is, what is P? It is phases, number of phases or phases are number of phases present in the system. Okay, so this is the meaning for F, C, P and other things. Now let us go into detail about the things, variables present in the system. Now first we are going to discuss about the P, letter P. What is P? It is phases, phase or number of phases. Okay, so what can be termed as a phase? What can be termed as a phase? Okay, any homogeneous, physically distinct part of a system which is bounded by a surface and is mechanically separable from other parts of the system. Okay, this may be fishy or this may be difficult to understand. We should be clear in 4 different points to know what is a phase. So what are the conditions to be a material as a phase? It should be homogeneous, first point. It should be physically distinct part of a system, second point. It is bounded by a surface, third point, which is mechanically separable from other parts of the system. If the part of a system is like this, if the part of a system is obeying 4 different points, for all these 4 different points, we can say that material is a phase, or that particular part is a phase. If there are different kinds of these 4 material present in the system, then different kinds of 4 parts are different phases. If a system consists of different materials and that different materials obeys all these 4 points, then we can say that all the 4 points, all the 4 parts are consisting a phase. Okay, we can understand clearly when we see some examples. Okay, so now we are going to discuss the examples. Okay, we have a atmosphere, good atmosphere, which consists of gaseous molecules. We are breathing in the atmosphere now. We are surrounded by different kinds of gaseous molecule. But we cannot say that here is only presence of oxygen, the presence of only oxygen atoms or molecules, or presence of only nitrogen or hydrogen, or carbon dioxide. We know that different kinds of gaseous molecules are surrounding us. We are just surrounded by different kinds of gaseous molecule, and they are not heterogeneous to each other. They are thoroughly mixed with one another. They are homogeneous. That is what I am trying to say now. Homogeneous, same throughout. They are uniform. There may be different when we go up in the atmosphere, when we go up in height. There may be concentration of oxygen may be less, but it is homogeneous now at normal pressure, at normal condition, and each and everything is a physically distinct part of a system. They are bounded by a surface. Of course, they are bounded by a surface, and we can separate the molecules from one part into other part. That is what called mechanically separable. Okay, so this consists a gas. There is only one phase. Consists a phase. So one phase. It is homogeneous. It is physically distinct. It is bounded by a surface. It is mechanically separable. So it is called one phase. A gaseous mixture consists of one phase. P is equal to 1. And in the case of a second example, when we mix water with sugar, or when we mix sugar with water, we will get, after stirring the NaCl or sugar, we will get a dissolved clear solution. And in the same case, if we mix sugar with water, we will get a homogeneous mixture after dissolving sugar in water. So even though there is presence of two different materials, two different chemicals, sugar is a different chemical, water is a H2O, and NaCl is a different chemical, and H2O is a different chemical. But when we mix together after stirring, it becomes a sugar solution. This one becomes a NaCl solution, but number of phases present in that is equal to 1. Only one phase. But there are, even though there is presence of two chemicals. Okay. And now we are going to a different example. When we add carbon tetrachloride with water, they do not mix with each other. They will stay in two different layers. If we add water with coconut oil, definitely we will get two different layers. Water with kerosene, we will get two different layers. They do not mix with each other. So those two chemicals are present in two different phases, since they are not homogeneous. Okay, in that case the number of phases P is equal to 2. Okay, since they do not mix with each other, water with oil, water with carbon tetrachloride, we can have innumerable numbers of examples. Okay, so we can have any number of examples. There may be more than two phases also possibly present. Okay, and when we add alcohol with water, when we add benzene with chloroform, they completely miscible with each other. They completely miscible with each other. So we are getting a homogeneous mixture as a resultant. So in that case, P will be equal to 1. P will be equal to 1. And for a chemical equilibrium condition, CaCO3 of a solid material which is in equilibrium with the CaO plus CO2. In that case, we are having two different solids and one gas. So totally solid and gas is present. Solid and gas is present, but both the solids are different from each other. Both the solids are different from each other, but they are solids. So two solids and one gas. So 2 plus 1 is equal to 3 phases. So two solid phases, one gaseous phase. Totally is equal to 3. So this is the right one. So this is what we can get an explanation in the part of phases. Thank you.